In this demonstration, we'll discuss how we are able to take signals from a Jaguar in the field, read its locational data, enrich it with third-party weather data, and use that to intelligently control the roof of the convertible. So this is the GENIVI Jaguar interface that shows the current status of the car's roof based on the current weather. So currently the car would, in this simulation, be near Boston, where we're pulling that the weather data is, although cold, no rain is forecasted, so the roof is open. In production, this would be linked to the GPS location of the car, but for testing, we want to have slightly more agility to be able to move the car around to different locations and simulate what would happen there for testing. So the whole Boston area is going to be pretty nice with the roof status open. But if we were to move the car to a simulated location down in Georgia, when it updates, you'll see that the roof closes due to the thunderstorms present in the area. The goal of this project is to show that we are able to take data in from the car, enrich it with third-party API information, in this example weather, and push commands back down to the car itself.
So this ingest processors group is what enables us to receive the data or events from the vehicle over HTTP currently using a REST interface. This could easily be extended to any protocol which you could make a NiFi processor out of. Immediately what we do here is first we just receive the raw HTTP request, right? Then we perform some real lightweight authentication and authorization with a shared secret. So we check this token, and then we're able to either immediately reject these messages, or we can pass them downstream and pass back a valid 200 HTTP response. From there, we immediately fork the stream off to different processor groups, and then we continue to send it downstream and collect it for HDFS storage. This HDFS storage could then later be used to build predictive algorithms and do long-term historical analysis against the data. So from that output port, which we forked that authenticated JSON, which we've received from the vehicle, we send this to a Kafka stream. This is just a write once principle where we attempt to where we place the data immediately into a Kafka topic so that other consumers can subscribe to that. And so the digital car simulator is effectively powered from a very simple map that we've created that allows us to drag pins around to update a vehicle's location. And it's also using the NiFi HTTP request handler. And it enables us to just take very simple messages directly from a JSON input and place them into updates in HBase.
Once these signals are received, we have to start ingesting them and storing them so we can analyze them and provide the output. But the main problem we encounter here is a scalability problem. As we're receiving different signals from different cars and different manufacturers, everybody will have different schemas. Some cars might have a more advanced infotainment unit, and some cars might have cameras that track the road. It'd become very difficult for a traditional organization to adapt the schemas every time a new type of car is released, especially if we plan to scale to a global setting. To fix this, we introduced the concept of a Schema'less Ods processor. This is the concept that we will take the message, evaluate what the manufacturers decided to call the different fields in the JSON, and store them as key value arrays inside of HBase. This enables us to, regardless of what the manufacturer does, provide the data in a meaningful fashion back to them without having to adjust our internal table structure. So, in the example that we have here, the operational data store will contain a unique car identifier such as the VIN, the date the message was received, the type of message or signal it was in this example, so an attribute by attribute basis, and the value of that attribute. And then regardless of what attributes are associated with which car, they will be made available to the manufacturer as is.
Here's where we perform scans of our own ODS to gather the latitude and longitude of the current vehicle's state. And this allows us to then send this data downstream to be enriched by other APIs such as weather.
So this latitude and longitude is passed to what we call the weather API lookup. Here we're invoking a third-party API This, in this example, is a outside service, but it could very easily be an internal business intelligence feed. And taking the latitude and longitude and looking up what the current conditions are and what the forecast will be. The forecast is then forked off to an updated forecast, which is passed downstream towards the roof controller, which will help open or close the roof, while the rest of it is processed through here, extracted, combined, and sent on its way to events out. The events out is then sent to the Schema'less ODS processor, much in the same way the car data is, and the updated forecast is sent towards the roof controller to make a determination if the roof should be opened or closed.
Here you can see we have two types of events coming both in and out of the roof controller. So we have forecast events that were being powered from the weather lookup, enriching the latitude and longitude of the vehicle. And then there's also the events out, which are any actions logically that we might decide to take on a car, such as things that this roof controllers will power. So the roof controllers takes the forecast enriched latitude and longitude and feeds it to the roof logic. The roof logic then just decides whether or not it should open or close the roof based on the actual weather. So we also send that right off to the ODS. And then right now, because this is being used for a demo, we filter this out to make sure that only the weather map is causing this action to take place. So then we take that success that says we need to perform an action and we send it through the event in input port. And we update a couple attributes on our flow file here, and then we send it off just with a post HTTP to the GENIVI RVI server, which helps make the call to the car. So here we take the event in flow files and update some headers, and then set the command that needs to take place on the car. As you can see over to the right, we also take a fork of all of the events, and we queue them up to a funnel that goes nowhere. We age this out over 6 hours, so that way we can see potential actions take place that would have triggered without actually having to always send them to the car. So then we take that command as well and we send it to the post HTTP processor. This then sends the command to the car via RVI to either open or close the roof.
The final part of this is how do we service all of this to an external dashboard such as that map we showed at the beginning of the demo. That is handled to another REST API where we're handling the requests. So we can receive requests, respond to options so the clients know what type of requests are available, and then basically run through the whole path and provide the results back out at the end. This can be used as in the aforementioned example to power a map, but it could also be used to power live dashboards through JavaScript.